So today, we're going to start Unit 2 on dynamics. I kind of introduced that a little bit on Friday, okay, where we're going to be talking about forces, right? We're going to be talking about work energy theorem, which is something, both of those things are a little bit from Science 10. Work energy theorem more from Science 10 than forces. Okay, we're going to go over forces, Newton's laws, first, second, and third, right? All that kind of stuff. Today is just going to be Newton's first law, which is defined in one word, inertia. We'll go over that in a little more detail. Okay, and then we'll be moving into tomorrow probably Newton's second law. Spend quite a bit of time on that because Newton's second law is big. Okay, there's still going to be some vector stuff in this unit. Still going to have to find the x's and y's and all of that. Okay, because force is a vector quantity, so that'll still be part of what we're doing. And then, like I say, we'll get into work energy theorem, which should hopefully seem familiar to you. Okay, because it is something you took in Science 10, but we'll see. It might have been something you missed because it was during online learning. Okay, so we'll be looking at that stuff there. So for today, we're going to look at what's meant by inertia. So here's like the easiest kind of definition or example of inertia. According to Newton's first law, this desk, provided I don't do anything to it, will stay right there. Well, duh, right? I mean, that's pretty obvious. But that's Newton's first law. Okay? The law of inertia says that an object at rest will remain at rest unless acted upon by an external unbalanced force. Okay?
This probably doesn't make sense, but like in different like atmospheres and stuff, is it possible that something never gets fully to rest?
That something never gets fully to rest.
Yes.
I don't know what the effect of atmospheres would be, but you could have different gravities and things like that.
Physics, you know, like how differently things accelerate and decelerate at different speeds because of like gravity.
Mm-hmm.
Would it be different in other places? So like
Newton's, yeah, okay, sorry, go, keep going.
So like would some things possibly never get to rest?
Yes. In the vacuum of space, once something gets moving, the other part of Newton's first law says that an object will continue to travel at a constant velocity unless acted upon by an external unbalanced force. So it works for both an object at rest and an object that's moving in a straight line. Right? Constant velocity means it has to be going in a straight line because velocity is a vector quantity. To turn something would require a push or a pull.
Let's just jump off of Sydney's thing for fun. Like the space thing that like floats around and like the international space, they just like floats around. Is that an example of that then?
No, the International Space Station is traveling at is actually not traveling at a constant velocity because it's moving in a circle, right? Constant velocity being straight line. To stay in orbit, what there actually is the force of gravity is always pulling the space station towards the Earth. But because it's going fast enough, it never gets any closer. So the distance it falls is equal to the distance the Earth curves away because the Earth's round. Okay? If you're a flat earther, I'm sorry, I'm not sorry. If you're a flat earther, that's crazy talk. Okay? There is zero scientific evidence to support a flat Earth. We have satellites that go around our very round Earth. Okay? So, if you get something, in order to get something into orbit, you have to make it go really fast. Fast enough that as it falls, the Earth curves away.
So, my phone is flush to the ground.
Yes, that is true.
Yeah, so
That does not mean the Earth is not round. We leveled this floor. And that's why you can't see forever, right? Like the horizon curves away. Okay.
How do they, like, with that ISS, that's what it's called, right?
The International Space Station.
Yeah. How do they get it to, in like that spot and know that spot where it just doesn't fall?
Okay, so what you do to get anything in orbit is obviously launch it on a rocket. Okay, and you get it. So a rocket, it looks like from Earth that it's always just going straight up, but actually there's a rollover maneuver that occurs at a certain altitude. So they go straight up for a while, and then like if it was the old space shuttle or something like that, they would roll. It would flip over onto its back, and it would start curving away. Okay, and so it would get into this kind of tangential arc that is the same as the Earth. And as long as it goes fast enough, like I say, it can't fall. So they would, take these spacecraft with the parts of the International Space Station up into orbit like that. Once they get them there, they can do whatever they want to them. Now they're in the vacuum of space. They're not going to slow down. They don't need a lot of, fuel to keep them there because there's nothing to slow them down. They can just maintain that orbit. Now, obviously, there's a little bit of maneuvering that it can do, but it's not going to jet itself to the moon, right? So, yeah, to answer your question, to put something in orbit, doesn't matter what, okay? Sputnik, which was like the size of a basketball, right, versus the International Space Station, is exactly the same physics. They both have to go the same speed. Yeah, if they stay in orbit. Yeah?
Yeah.
Okay. All right, so Newton's first law, like we said, something at rest remains at rest unless acted on by an external unbalanced force. Something will continue to travel at a constant velocity until acted upon by an external unbalanced force. This is an astronaut's worst nightmare. Okay? Newton's first law is the thing that can get an astronaut killed in space. Because in space, no one can hear you scream. But also, you have no way to produce a force that can move you around. Unless you have like the little maneuvering thrusters on your spacesuit, which all spacesuits have, but they only have a limited amount of fuel. Right? So if I run out of maneuvering fuel, I am going to continue to travel at that velocity until something stops me. And it's not going to be anything I can do. I can flail around and scream and holler and it won't do any good. Okay? I am going to continue to travel at that velocity. But if you've seen The Martian, okay, it's why Mark Watney had to cut the hole in his glove. Right? He was committed. He had left his launch vehicle and was committed to this trajectory. Now it was eventually going to re-encounter Mars because he was still in Mars gravity. But in order to change his trajectory, he needed to exert a force. But he didn't have any maneuvering jets on his suit. So what he did is he cut his glove and then just opened his hand so that the escaping air could push him around. Okay? Now, that's all well and good until you run out of air. But, I mean, it was in life where he was going to die if he didn't. So it was, pick your poison. So that's what he did, and that's why it worked. Well, theoretically it worked. I mean, it would have never worked. But it worked because it was movies. Okay? But the physics behind it is sound. The reality of it is a little less so. Okay? Does that sort of make sense? He had some way to exert that unbalanced force.
Like if you've ever watched like Interstellar,
Mm-hmm.
how does time get altered? Like,
That's a totally different thing, but it has to do with speed and gravity. The closer to a large gravity well you are, the more that gravity distorts space and time. So there's even a difference in, like, if someone has a watch on Earth and a watch on International Space Station, you sync them up, within a little while they'll be out of sync. Okay? Because we're closer to the gravity well of the Earth than they are, time is ever so slightly different. Yeah.
would they age slower or faster?
It's not about them aging slower or faster, it's about they would age at the same rate that they experience, but because time is slower for one of them, then it's like that. Yeah. All right, and with Interstellar, they were next to that big black hole, right? That was the big deal, was the big black hole was altering space and time. Okay, so the inertia of an object is related to its mass. The more massive an object is, the more inertia it has. Okay? So, if I've got this desk, it's pretty easy for me to just pick it up and move it. It's not very massive. Now, if I walk up to a rail car, like down in the rail yard, I'll just move that. I mean, I can because I'm me, but most people wouldn't be able to. You can't. It's too big. It has way more inertia. Okay? It's why you or I don't just hook a rope to it and start walking along, pull it along behind us. We have to have this massive big train engine that does it instead because it has more inertia. Its tendency to sit still is much greater than my tendency to sit still because it's much more massive. Okay, does that sort of make sense? Okay. All right, any change in inertia, whether it's stationary or moving at a constant velocity, requires a force, even just to turn something. All right? Think of this. You're driving down the road, it's icy, and you want to turn left, okay? You try to turn left, but it's too icy. What do? You just go straight, right? If you slam on the brakes, or just touch the brakes even just to slow down and then turn your wheel, your car just keeps going straight. It's inertia. there is no unbalanced force that's trying to help you turn. What force normally helps you turn? Friction, yeah. When you turn your wheels, the frictional forces help you around the corner. They keep you from sliding. When that friction is gone, you obey Newton's first law. And you go straight into whatever is there. Okay? You gotta keep that in mind. It's Newton's first law that causes car accidents on icy roads. Okay? If there's no friction to alter your speed or cause an acceleration, you continue to obey Newton's first law. All right? Okay. So, what's a force? We gotta start out with that because that's the most important thing in this unit. Forces. Okay? A force, very simply, a push or a pull. Okay? It can be a push or a pull. Okay? It's exerted on the object either directly or indirectly. All right? Directly would be I walk up and push. Okay? Or I walk up and pull. That would be a direct application of force. An indirect application of force would be something like gravity. Earth does not need to be in direct contact with something to exert a gravitational force on it. In fact, I can exert a gravitational force on you without touching you. It's just incredibly puny and it's completely obliterated by the Earth's gravitational force because the Earth's way bigger. Okay? But it's true. Okay? So there's like field forces that can exert a force indirectly without being in direct contact. And then there's direct forces, okay? Ones that are pushing directly or pulling directly. Okay? All right. Now, like I said, force is a vector quantity, so forces can be angled. Okay. If we have a cable, like here between the tow truck and the car, okay, there would be a tensional force in the cable that can exert a pulling force on the car. Okay. If you have like a baseball, which is just a projectile after it's been hit, then we've got the field force of gravity constantly pulling that ball back down to the earth. Or if you've got a bulldozer pushing something, okay, you have a direct pushing force between the bulldozer and whatever it is going to push. Okay? Everybody all right with that? Okay. Okay, so mass is also important. Okay, a massive super tanker like that one has way more inertia than the penny. They still both obey Newton's first law. Okay? If they're both stationary, they're going to stay stationary until acted upon by an external unbalanced force. It's just the reality of that unbalanced force has to be way bigger in order to cause a similar acceleration in the supertanker. Now, if I had both the supertanker and the penny in outer space, could I move the supertanker? Yep, I could. Right? If I pushed on the supertanker, it would move. Not much. Okay? Its acceleration is, again, correspondingly small compared to its mass. If I exert that same force on the penny flies away, right? But if I exert a force and there's nothing else to stop that supertanker, I would get it to move ever so slightly, right? But it would move. So would I, right? Because Newton's third law says if I push on the supertanker pushes back on me. And since I'm much less massive, all that force really ends up doing is this. The wall moved a little, right? You heard it crack, but okay, I moved a lot more because I'm less massive than the wall. Okay, there was an acceleration for both of us, but it was bigger on me because I just have a small mass. All right, now that comes into play when we're talking about collision safety. If a semi-truck and a smart car get in a collision, who wins? Why? It's bigger. It's simply bigger. And make no mistake, in every collision, there's a winner and a loser. Okay? And the winner is invariably the more massive of the two vehicles. Right? Your most important safety feature in your car is mass. Okay? If you're bigger, you'll win. If you're smaller, then you got to depend on all your secondary safety devices. Your seatbelts, most important. Okay? Your airbags, secondary. Okay, curtain airbags, all the other stuff. Okay, crumple zones on the car, all of that kind of stuff. Those are all secondary to mass. Okay, you run a smart car head on into a semi-truck, it doesn't matter how many airbags, or how good the seatbelt, or how much crumple, because there's not much crumple in a smart car. Okay, you're the loser. Okay, you have less mass. All right, anyone been in a car crash? Okay, yeah, I've been in a couple myself. Okay, I had a lady turn left, right in front of me, okay? And I was driving our Ford Expedition at that time, okay? She was driving just a little, like, sedan, and she turned left in front of me. How she didn't see me, I'll never understand, but, okay, turned left, I never even had a chance. There were, like, no skid marks on the road, okay? But I was going 60 kilometers an hour. She was going maybe 15 because she was in the process of turning, okay? Her airbags all detonated, okay? Her car was crumpled down to nothing, okay? And she was fine, luckily, but you know, like, her car was a write-off. I had to replace the headlight assembly and the fender. Why? Like, my airbags didn't go off at all because I didn't have sufficient enough acceleration as a result of hitting her to set off the sensor. Why? More massive. Okay? Bigger. That's why when you have kids, think about that. You want them to be really safe in the car? Bigger is better. Okay? It just is. I'm not trying to say that to support oil and gas or anything like that, although, you know, it's kind of what makes Alberta run, but okay, it's you know, bigger is better. Bigger is going to be safer. I mean, you don't see too often where a guy driving a semi-truck gets hurt too bad, okay, in a crash.
I had was at an intersection. I was going, and a lady swapped lanes mid-intersection, and the front end of my car was badly damaged, and same like what happened to you. Her airbags went off, mine didn't, because I have an SUV, and she got a write-off. I had to pay for to get so much repaired, and I was so angry because I was like, you can't.
Yeah, you're not supposed to change lanes in an intersection. That's exactly why.
Get a dash cam.
Want to see a cool example?
Yeah, I know.
I was just going to show you guys. I got a few videos.
Because of that, I purposely went on a bog dash cam. It's like, if this ever happens again.
I see that on every birthday, but every time.
Okay, so I'm going to show you a few of the videos I've got. But the first one I'm going to show you is the smart car versus concrete. Okay? Yeah. So what we just saw was the smart car hitting the Mercedes. Okay? And what we saw was the smart car ended up moving backwards. Okay? So all of this is governed by a formula that's fairly familiar to us. Okay? The acceleration you experience is what's going to hurt you. The greater the acceleration, the greater the potential for injury. Okay? So the things that can affect how much acceleration you feel are your initial velocity, which you don't have a lot of control over. It's how fast you were going when the collision started. Maybe you got on the brakes before and you reduced your velocity a little bit, but you really don't have a lot of control over that. VF, super important. You don't want this to be a negative number. Okay? If VF is a negative number, A is going to be big because you'll have VF minus this and you'll have a big acceleration, right? Because the difference between those two things will be very large. If VF is still a positive number, that means you continue to move forward. Your velocity changed less. And since the change in velocity is directly related to your acceleration, you would feel less acceleration and be less likely to be injured. Does that make sense, everybody? Okay, so you've got that part of the equation. And then you've got this part of the equation. Most of your safety features are designed around making the crash take longer, which is counterintuitive. You think, I just want the crash to be over. Okay, but you actually want the crash to happen slowly, because the bigger T is, what happens to A? Smaller, right? I'm dividing by T, so the bigger T is, the smaller A will be. Everybody follow my reasoning there? Okay, so your seatbelt, designed to make T bigger, right? You move forwards, okay? You hit the seatbelt, and the seatbelt stops you. Now, it does stretch a little bit, okay? If you're going more than 50 kilometers an hour and your car is not a write-off, you'll have to get the seatbelts replaced because they are slightly elastic, okay? And they will stretch, right? That's going to make your change in velocity happen over a slightly longer time. Airbags, same deal, right? When you hit an airbag, you slow down more slowly, okay? If you hit the steering wheel, you slow down more fast, okay? Now, if you look in like well, not even your parents' generation, but maybe your grandparents' generation, okay? Anybody who was in a car crash, they had a very similar scar, right here, right on the hairline, because that was pre-airbags and pre-collapsible steering wheels. Steering wheels were hard, rigid objects, and if you got in a crash, and of course then seatbelts didn't have the shoulder strap, they were just around the waist, you would go forward into the steering wheel, okay? Cause concussions, okay? Lacerations or scalpings, okay? Because you hit the steering wheel and just, people get their scalps peeled right back, okay? Because the steering wheels were hard, right? So in the late 70s and early 80s, it became standard to make a collapsible steering wheel. All right, don't try this, but if you hit the top of the steering wheel really hard, okay, it should cave in. They're designed to do that, okay? Especially in a car pre-airbag. Not that you would drive one of those now, but okay, if you're like late 70s, early 80s, pre-airbags, okay, if you hit the steering wheel will collapse. They were also made fatter and cushioned, okay, as opposed to these hard wooden, okay, or metal, okay, kind of things. They were rigid and hard. Okay, so you got airbags that increase the amount of time. The crumple zone in your car, right? Instead of the car stopping immediately because it's a hard, rigid object, it slows down more gradually because it changes shape and crumples up. Okay, the crumple zones are designed to make T longer. I'm not talking seconds. We're talking hundredths of a second, maybe tenths of a second if you're lucky. But it makes a big difference. Okay, in terms of the amount of acceleration and thus the amount of force that is exerted on your body in the crash. Okay, so all of those things are designed around time. All the safety devices in your car are designed around time. Your car's mass affects the time. Okay, the more massive you are, the less the top will be. Okay, the smaller you are, the bigger the top will be. Right, so the top part of this equation is basically part of what can hurt you. If this is a big number, VF minus VI, A is going to be larger. Time was essentially the same for both the smart car and that other car. But there was a greater change in velocity for the second car because it literally bounced off of the wall. Okay? VF was a high negative number. Whereas for the smart car, VF was essentially 0. Right? It didn't bounce off of the concrete. It hit the concrete and kind of slid along it, came to a stop. Right? That's better than bouncing off. Right? Bouncing off is going to result in a greater acceleration. Right? So you don't want that. And that was the problem early on with cars. They were built like tanks. Okay? People are like, well, if I get in a crash, I don't want to have to fix my car. Right? I want to just take a ball peen hammer, pound out that dent, and be done with it. Okay? Well, that's all well and good, except you're not going to be around to do that if your car doesn't change shape and absorb some of those crash forces for you. Okay? So old cars, they would hit, and they didn't change shape. They were very elastic collisions, which means they would bounce off of each other. Okay? There wasn't a lot of mangling, okay, of the cars like there is now.
So did
All
you
right.
hit in your car, or did you hit something too hard inside your car in that case?
Yes. Yeah. The crash forces are transferred basically to you. Yeah. Okay, so that's what we're looking at. Okay, that's part of Newton's first law. Okay, inertia is affected by mass. Okay, and any change in velocity is going to be an acceleration, and that's going to be caused by a force. All right. So Newton's first law, it talks a bit about that. Now, the part of Newton's first law where if you have an object in motion, it might remain in motion, as I was saying, is every astronaut's worst nightmare. Becoming separated from your vehicle in space without any means of propulsion means that you're just going to float away. And there'll be nothing that you can do about it, okay, because you have no way to exert a force that can change your velocity. Right? All right, now, mass and weight, are they the same thing? They are not. Okay? In our society, we talk about them like they are. Because if I ask you how much you weigh, you tell me how many pounds or kilograms you are. That is not your weight. That is your mass. I can lose weight by going to the moon. Be a big change in my weight. I'll weigh 1/6 what I weigh here. But there won't be any less of me. Okay? When we say I'm going to lose weight or I'm going to gain weight, no, we're not. We're gaining mass or losing mass. We're getting more or less of us, okay? More or less matter. But weight has to do with gravity. right? So your weight is dependent on your mass, but also on the polar gravity. Okay? It's a force. It is the force of gravity pulling on your mass. It is different than your mass, which is how much of you there is. It doesn't matter where I go, even if I'm weightless, I'm not massless. Okay? I might not have any weight because there's no gravity pulling on me, but I still have mass. Okay? And that can be a problem if I'm moving through the International Space Station and all of a sudden somebody pops up from another spot and I can't stop. Okay? Well, I'm going to hit them because I have mass, and I'm going to cause an acceleration because I've got mass. Okay? I may not have any weight, but there's still me there. Okay? So mass and weight are two different things. Okay? So when you go to lift weights, you're not really lifting weights. You're lifting masses. Doesn't sound as cool to say it that way, so we don't. Okay? But if I went onto the International Space Station, I could be like one of those roid monkeys at the gym, okay, who like puts like 5 plates on each side for the bench press, and I could take that thing off and I could lift it. But what would happen? I'd follow it. Okay? Think about it. Newton's first law. So I put the bench press thing down on my chest, but I'm on the International Space Station where there's no gravity, so it's not hurting me. It doesn't matter how much weight is on there, how much mass is on there, I can move it. And then its inertia will take me right along. Because it's usually gravity that stops the bar, not you. Okay? It's just that you can't push anymore, so it stops because of gravity, and you just hold it there. Okay? But in space, it'll just keep going. And if you don't let go, you'll go with it. That's why they don't use weights on the International Space Station. They use a Bowflex. Well, it's like a Bowflex, not a Bowflex brand, but it's like that. It's a resistance machine, because resistance doesn't require gravity to work.
Is there a weight and mass that are equal to each other on Earth? Like, is it-
No, they're dependent on each other, but no, good question, not equal to each other. Okay? We calculate our weight. Our weight is the force of gravity. We calculate that by taking our mass and multiplying by the acceleration due to gravity. So whatever your mass is in kilograms times 9.81. That will give you your weight, and it'll be in newtons, because that's the units for force. This is a little joke I play on people at parties, okay? Because sometimes people are socially inept, and they ask you like really inappropriate questions, like how much do you weigh? You should never ask somebody that. Okay? That's not a polite question, right? So what I do is I tell them exactly what I weigh. I tell them I weigh 785 newtons. And they look at me and chuckle uncomfortably and walk away.
Good.
And I'm like, yeah, that's right. And
You walk away.
I told you the absolute truth. I told you what I weigh, and I made you feel uncomfortable for asking me. I made you also think that I'm weird, but that's fine, I am. Okay? That's me, I can live with that. Right? But your weight is the force of gravity pulling on your mass, and it changes depending on where you are. Okay? Because the Earth is round, remember that, okay? It's not perfectly round. It's not flat, okay, because that's crazy. But it's also not perfectly round. It's actually a little bit ellipsoid. All right? So the acceleration due to gravity is dependent, okay, on how far from the center of the Earth you are. So you weigh more at the poles than you do at the equator, because the Earth is squished a little bit. Okay, so at sea level at the equator, you are actually further from the center of the Earth than you are if you're standing on the top of Mount Everest. That's how oblong the Earth is. Okay? You're actually further from the center of the Earth on the beach at sea level than you are standing on the highest point on the Earth's surface. Okay? So how far away from the center of the Earth you are can affect this. So I can weigh different amounts depending on where I are. Now, I'm not saying it's like 10 pounds. It's not. Okay? We're talking, maybe a couple of grams here or there. It's not a huge amount, but it's a slight difference.
Does that also mean like depending on where you live, you can have the potential to be taller?
Yes, that is true, but not significant. Okay, again, we're talking grams at the most here. It's your genetics and your diet that are far more likely to determine how tall you're going to be than gravity. Now, if I grew up on Mars, I would probably be significantly taller, right? Or if I grew up on Jupiter, I'd, well, be dead, but shorter. Right? Yeah. Okay, so that's the difference. Mass, how much of you there is, how much matter you are. Okay, weight, how much gravity pulls on that. It's a force versus mass. Okay, so important to know the difference there. All right, so to understand Newton's first law, if you're thinking of like hockey or paint dry, I mean curling, but if you've ever like watched that, okay, it's, you know, you slide the rock and it slides down the ice. Now, if the ice was perfectly frictionless, probably more fun to watch, because the rock would not what? It would never stop, right? It's the small amount of friction between the rock and the ice that causes it to stop. Okay? Same with hockey, okay? The ice is very slippery, but it's not frictionless. Okay? But if it was frictionless, once that puck is struck, that puck is going to remain in motion at that constant velocity until something else acts on it. Okay? And that's what happens in space. In space, there's no friction. Right? You're in the vacuum of space. If you cannot exert a force in an opposite direction, you continue to move at that constant velocity forever. Okay? Until you get close enough to some gravitational body to be pulled in. So I'm going to show you a video about that here. So there, now you're seeing some of the like real world kind of applications, Newton's first law. Okay, we say real world, we looked at the space ones, but I mean, it's still real world. All right, so Newton's first law says this: an object at rest will remain at rest. An object traveling along at a constant speed will continue to do so unless acted upon by a net force or unbalanced force. Right? So when we were talking about the desk right at the beginning of class, are there forces acting on the desk right now? Gravity's acting on the desk. What else? That's a tough one, right? Gravity's easy, right? We're like, oh yeah, gravity's acting on it. But if only gravity was acting on it, what should the desk be doing? Yeah, or falling. What's keeping it from falling? The floor. Okay. So in any situation, this has to do with Newton's third law, okay, which we're not at yet, but in any situation, if this is the desk, gravity pulls down on the desk, and the floor pushes up with an equal and opposite force. Okay, that's why we call it the normal force. It keeps things normal. Okay, without the normal force, everything would be flying all over the place. Okay, so there are no unbalanced or net forces for the desk because this force and this force are equal and opposite, so they cancel each other out, and there's no net force. Okay, so net means the sum, the vector sum of all of them. Okay? If you have a part-time job, you see that word in front of your pay. Right? You have your gross pay, which is that really nice number, right? And then you have all like the government extortion, and then you have your net pay, which is an unfortunately sad smaller number. Okay? Well, the net is what you have when everything else is taken away. Okay? So in this case, the net force is 0 because these two things cancel each other out. Okay? So in any situation where the net force is 0, the object is either at rest or traveling at a constant velocity. Okay? And that includes direction, so straight line. Okay? So the first law used the phrase net force. That's what we were just talking about. The net force is the vector sum of all the forces acting on the object. So if I'm looking at this situation here where I've got a book sitting on a desk, and I push it this way with 20 newtons of force, and friction resists with 18 newtons of force, what's my net force? 2 newtons. It's going to accelerate to the left. Okay, because there's a net force, an unbalanced force now to the left. So this object does not sit still, it does not travel at a constant velocity, it accelerates to the left. As a result. All right, everybody okay with that idea? All right, so any net force causes an acceleration, but that acceleration is proportional to your mass. Right? So if I put let's say a net force of 25 newtons on a penny, the penny will go flying. If I put a net force of 25 newtons on a book, the book will probably slide pretty quickly. Okay? Put it on a bike, the bike's going to accelerate fairly quickly. Put it on a car, the car is not going to do very much. Okay? Put it on a plane, not going to notice it at all. Put it on a super tanker, not going to notice it at all. Okay? Now, again, in space, all of those objects would accelerate as a result of that 25 newton force, but their accelerations would look very, very different. So mass affects your acceleration because it affects your inertia. All right, so quantitatively, the inertia of an object is measured by its mass, such as that of the train, indicating a large inertia. So inertia is the natural tendency of an object to remain at rest or in motion at a constant speed along a straight line. The mass of an object is the quantitative measure of inertia. That's Newton's first law. Okay, now here's the interesting thing about Newton's first law. There's no math. There's no formula for Newton's first law. We just have to understand it. Okay? We have to know that if there's no net force, the object stays put or continues to travel at a constant velocity.
So, when we watched that video that was like the feather and the vertical all in the same rate,
Yep.
if there wasn't like a force acting on them and they weighed different, how did they fall at the same speed?
Well, there was a force acting on it, it was gravity. Okay? But gravity has that, like, once they remove the air, the acceleration due to gravity is the same for all objects. Acceleration due to gravity is dependent on where you are, not how heavy you are. Okay? Like a piano and a beach ball would fall at the same rate. Bowling ball and the feather fall at the same rate if there's no air resistance, right? The only force acting on them is gravity, and it produces the same acceleration. Now, what would be different is this. Which one would you stand under? Okay? G, the acceleration, is the same for all objects. The weight is what would hurt. Okay? They'll be moving at the same speed because they have the same acceleration, but I'd rather get hit by the feather because the force it would exert on me would be much less than the bowling ball. Yeah? Yes. All right, so that's what we need to know about Newton's first law, okay? Just that mass is affected by inertia, okay, or sorry, inertia is affected by mass, okay, and that if there's no net force, then everything stays the way it is, either at rest or at a constant velocity. As soon as there's a net force, then there will be a change in velocity, and that's Newton's second law. Okay, and that's what we'll move on to tomorrow. Okay, now, here's another application of Newton's first law. It's how your seatbelt works. Okay, your seatbelt activates because of inertia. So inside the little kind of reel that's inside of your seatbelt, okay, there's the ratcheted wheel that your seatbelt takes up onto. Okay, then there's a locking bar and a pendulum. Okay, so the pendulum works like this. Okay, so you're driving along in your car at a constant velocity and then you stop. What happens to the pendulum? Keeps going. Newton's first law, right? The pendulum swings forward. Well, for your seatbelt, when the pendulum swings forward, it pivots and tilts the locking bar into position to prevent your seatbelt from unraveling. Okay, that's what stops your seatbelt in a crash. It is completely infallible because you cannot defeat Newton's first law. Okay, it will happen. It's not based on a sensor. Okay, it's not dependent on anything electronic. It's just dependent on simple physics, which means it's 100% reliable. Okay, so it moves into position and stops the seatbelt from unraveling. Okay, now your airbags and things like that are based on accelerometers, which work under a similar idea. Okay, when you tilt your phone reorients the screen, right? How does it do that? Yeah, there's a gyro inside. What a gyro is basically it's a conducting, like a small metal ball. Okay, and when you turn the phone, that ball goes down because of gravity, and it makes contact with a different switch, which tells your phone, oh, now you're oriented this way, and flips the screen. Well, your airbags work on a similar idea. There's a metal ball, and it's surrounded by a conductive wire cage. If you stop at a certain acceleration, that ball will go forward and complete the circuit that detonates your airbag, right? But you have to produce a certain acceleration for it to work, okay? So they don't always go off. If it's not a serious enough crash, you don't need the airbags. The airbags don't explode because that metal ball doesn't move far enough ahead to complete the circuit, okay? And the same works from behind, okay? Your side curtain airbags, same thing, okay? They detonate. If you get in a really bad crash, the ball just goes around and activates everything, and everything blows up. Okay, but in a small crash, it'll only activate the ones that are necessary. Okay? that ball can complete the circuit for, right? Early airbags were actually on a contact switch. So there was a switch embedded in the bumper. If you kicked the car, you could set it off. Okay, so you can imagine that didn't last for very long. Okay? There's actually like a video of this old lady crossing the street in front of this guy in a convertible, and she's taking forever. The guy's honking at her, it was just a total jerk move, but he's honking, she's just really, really slow. Finally, she loses and takes her purse and swings it at the front of the car, and the airbag goes off in his face like instant karma. Okay? Yeah, but they don't use a contact sensor anymore because of exactly that reason. Somebody could detonate your airbag if they're a bad parallel parker. And you're not even in the car, and they can, do that parking by sound thing that some people do. You ever seen that? It's annoying. Both park by sound. Dunk, oh, I'm there. Dunk, oh, I'm there. Yeah. Don't do that. Yeah, so they used to have them that way, and of course they would detonate when they weren't needed, okay, which could be, that could cause an accident as opposed to save you from one. So now they're all based on an accelerometer, it's all computerized. Okay? But your seatbelt still works. Okay, on this. Okay, I think that's it. All right, so we don't have any of these. We're not going to do these because they're all to do with Newton's second law. So we'll talk about those tomorrow. We'll leave it there for today. So no quiz tomorrow. Because I don't have anything there's no problems I can give you for this. There's no math for Newton's first law. So no quiz tomorrow.